No, we don't.
Do they offer that at UC College?
Not that I've seen. The problem is it's a 300 level class. We're kind of restricted to 200 level class.
Because it says on the sheet that you should be talking
For which?
For pre-mechanical engineering for school.
Yeah. You have to do it at summer school at OSU. Yeah, for summer school at OSU, I'm pretty sure of that. I think I don't know if on their schedule if they have technical report writing in the first 2 years. So I think there's room in your schedule to fit it in. At OSU. If just because you might take at least one class here that you wouldn't normally if you were an OSU student. So, but I'm not even entirely sure that. So let's have a look at some of this homework that's coming due. So we got, now there are those two problems, those relative acceleration problems that we went over. That was Tuesday. And there's also these, are these due Wednesday or Monday? I can't remember. I think these are due Monday too. I think I assigned them for Monday. So let's have a look. These are moment of inertia problems, which we're going to start using here. These ideas. So let's have a look. All right, now this one you're supposed to do two ways. What you got there is a disk with a hole in it. So I asked you to do it with calculus and using the formulas on the formula sheet on the back. So what you would do with this, if you're going to do it with calculus, is just start to put an integral together, because that's how you would have to do it. You'd put together a series of rings is how you do it. So what you would have there is the basic definition of I is r squared dm. Okay, so you need to come up with an integral that will express that. Now, what you would do with that then is you would take this thing, you would start from that central axis and measure out, and where you would measure out to would be a ring. Okay, and the thickness of that ring would be dr. So what you would want then for I would be adding up those distances r that you come out. Then you'd want the area of the ring. Think of taking that ring and cutting it and laying it out flat. What it would be then would be a very long, thin rectangle if you were to do that. And the length of the thing would be 2 pi r. See, that would be the length of the ring. So that would be the area. So we got r squared times 2 pi r. Okay. Now that's the length actually. We're multiplying the length by the thickness is dr. That would get you the area. And then what do you got there? You've got a thickness. I'd keep this in meters, I think, so 0.05 meters. That's the thickness of the ring, so that gets you the volume. And then you've got the density, 2,400 kilograms per meter cubed. Okay. And then you got a dr on there. Okay. So that's how I would start with this, is to get that integral set up. Now you're going to have to figure out the limits to use on that. So what we've got is, let's see, 2,400 Then we got 2 pi r. Let's see. R squared dm, 240 pi. Oh, okay, so 2 times 0.05 is 0.1 times 2400 is 240. So I'd pull that 240 out, I'd pull the pi out, and then you would be left with what's behind there, and that's r cubed dr. Okay. So that's what you're going to end up with. And what we're doing here is I sub z. So you'll need to integrate this thing, okay? So you're going to have to figure out what these limits of integration are. Limits of integration indicate where you start integrating and where you finish. So I always think of it as an integral as being a computer program that tells you to go out a certain distance and do some sort of mathematical operations. In this case, we've done those things. We're going to go out a distance r. We're going to take square the r, multiply it by another r, so that will get us r cubed. Multiply it by 2 pi times 0.05 times 2400, and then times the thickness, all right? So you'll have to figure out those limits there to plug into that thing, and then evaluate the integral. And when you do that, what you ought to come up with is 0.00548, and the units on that will be kilogram meter squared. Okay. So are we doing all right with that? Any questions on that? All right, now I'd also like you to do this one with using the tables on the back of your formula sheet. Now, if you look there, what you'll see is a disk, okay? And that's the model that you want to use for this, of course, is a disk, something like that. And then you'd want to use that axis that comes out normal to the face of the disk. So that's how we'd like to approach this one here. Now, when you're doing this, what you're going to want to do here is use I for the entire disk, the whole thing, then subtract off I for the cutout. Okay, you can't shortcut that. You can't like find the volume of the entire disk minus the cutout, then find I for that. That really won't work. You have to get I for the entire disk, then subtract off I for the cutout, okay? It has to be done like that. So what you've got then, I for that disk will be 1/2 mr squared, okay? So I will be 1/2 mr squared. Okay? So that's the formula you're going to work with. So what you need to do here is to find the moment of inertia for the entire disk. Now that thing's going to have an outer radius of what, 0.075 meters. So you're going to have to find the mass of the thing, okay? So the mass of the disk what's that going to be? That thing has an area of pi times r, and that's going to be 0.075 meters squared. So there's the area. Multiply that by the depth, and you'll get the volume. So that's 0.05 meters. So now you got the volume. and then you can multiply that by 2,400 kilogram per cubic meter, okay? So that's pi r squared times the depth, that gets you the volume, then multiply it by the density. And that'll get you the mass of the entire disk. So when you run their numbers on that, you should be able to come up with the mass. So it's 2.12 kilograms, okay? So what you're going to do then to find I sub z is you're going to use that 1/2 mr squared formula. So that'll just be 1/2 times 2.12 kilograms times the outer radius, which is 0.075 meters squared. Okay, so and this again will be for the entire disk. Okay, so I sub z for that figure is going to be this term right here. And when you calculate that, that'll be 0.005965. And the units on that's kind of funny. It's kilogram meters squared. So if you want IZZ for the figure, what you're going to do is take 0.005965 and subtract off 1/2 mass of the cutout times the radius of the cutout, okay? And that'll be squared. And when you run those numbers, what you get is 0.00548, just like before. So we're just doing the same problem two different ways. Okay, so I'm just doing a bit of calculus there and then also some algebra. So we got any questions with that? You doing all right? Okay. All right, so that's the first one there. All right, now the second one is just using the transfer axis theorem. What you've got there is you've got a rectangle, okay? And if we look at it from the top, what you're going to see is something like that. I don't know, can I make that 3D? Yeah, I guess I can, something like that. And then we're going to have A. This might be an easier way to look at it. So here's the axis A right there. You want to find I sub A, and what that'll be, it'll be I sub G plus MD squared, okay? Now, to figure out where G is, of course, that's going to be in the middle of the plate. So G will be right there. So what you're going to want to find then is that two-dimensional distance to A. So that would be D right there. Okay. Now, when you look at your formula sheet, what you would see there will be on the back. is you've got a rectangle and you need to find the moment of inertia for the rectangle. And I don't quite remember how the thing's drawn up. Is it something like that? Okay. All right, there we go. Now, what you would have then would be three centroidal axes. One that goes through the center of gravity like that, another that goes through the center of gravity like that, and a last one that goes through like that. So which one of those is the one that you would use to calculate the moment of inertia of this shape about its center of gravity? Yeah, it's the last one, okay? So don't be fooled by the fact that it's oriented differently than the sketch we're working with. Just look at how the geometry works. What we're looking for is an axis normal to the big flat face on the rectangular prism. That's what we're looking for here. That's what we want, okay? So we've got that, okay? So we good with that? So you're going to want to use that one. And I think, is that I sub z there? Is that what they call it? I think that's what they call it. I sub gz or something? So that should be 1/12 m a squared plus b squared? Okay, thanks. All right. Now you've got the dimensions on your sketch there. So you can go ahead and find that. What you're going to have for our particular example is the volume, when you work that out, is 48 cubic centimeters, is how I work that out. The density is given in grams per centimeter cubed. So the mass then is 2592 grams. Okay. Now, what you want on that thing is you want to go to the rectangle. Here's G. You just want to take it off to point A over here. Now, the fact it's at an angle doesn't have to do with anything, okay? It's just the distance that matters. So you're going to want that distance there. And so you've got basically, you can get these dimensions there. What, 3 by 4, I think. Okay, so you can find D. Yeah, it's just pretty straight up. Yeah, nothing fancy about it. It's just you just want that straight distance from G to A. But then you're going to, okay, and then what you're going to do here is you're going to get the total then. So I sub A will be 1/12 times the mass, which is 2592 grams, times a squared plus b squared, okay? And then plus the mass, which again is 2592 grams, times d squared. And when you combine those things, you'll get 86,400. Okay? So you just find the 1/12 m a squared plus b squared. That's I sub g, the moment of inertia about the centroid. And then you add m, the mass, times the offset distance between g and a quantity squared there, okay? So we got any questions on that? Okay. Now the last one is probably the most involved of the three, because you've got a composite shape there with kind of an axis you got to work with there. So Okay, so what you're going to want to do on this thing is I would set up a table on it. It's got enough going on with it where, that's probably what I would do. So what I want to do here is I'm going to want to find the moments of inertia of these two shapes. And the two shapes are a full rectangular plate that's, 18 by 12. So that would put the center of gravity for that thing right about there. So you're going to want this distance like that, okay? And then you're going to want to go for the full plate. What you're going to want to do is find I sub g plus md squared, and then you've got the circular cutout. That's going to be minus pi r squared for the area there, but you'll get an I sub g for that, okay, plus md squared. And then I for the assembly, let's call it, meaning composite parts there, will be IG for the plate, or excuse me, I for the plate, minus I for the circular cutout. So that's how that'll work. Okay. So you find the full moment of inertia for the plate as though it has no cutout, as though it's one entire solid plate, and then you find I for the solid material you're cutting out, and you subtract it. That's how that goes. Okay. So I would just set up a table, volume, mass, I sub g, offset distance, md squared, and then IG plus md squared. All right. And then I just walk on through it. Now the important thing there with that circular cutout is it's a cutout. So the volume, the mass, I sub g, and the md squared terms are all negative. Okay. So the volume there is going to be minus, again, because it's a cutout, pi r squared, so r is 0.03. And then you've got times the depth, which is 0.015. It's 1.5 centimeters for the depth. That dimension is right there. Okay. So pi r squared times the depth. And that's going to be negative 0.0000424. Not very big, but it's where we start with. And then we'll factor that up by the density, 400 kilograms per cubic meter, and that'll get us to negative 0.1696. So there's the mass. Now for a circle, when you take moments of inertia of a circle about, or a disk, I guess I should say, about its own centroid like that, what I sub g is 1/2 mr squared. Okay, so that's what I'm doing right here. I'm taking 1/2 times the mass times that radius squared, and it's a negative, so I put a negative out in front of it. Okay. All right, what I want next here is that offset distance d, which is that distance right there. You're given a number of dimensions to find it, so you got, what, a total of 15 over, so that'll be 15 centimeters over. Then you come back 8, so that'll be 7 centimeter distance there, so that's equal to d. So d is 7 centimeters. Okay. 15 over, 8 back. That gets you from that axis to the center of the circle. I've got that in meters, so it's 0.07. And then we get 0.0000831 when we take m times d squared. So that's the negative 0.1696 times 0.07 squared. So that'll get you the md squared term. So then what you do is you'll take IG, which is negative, and the md squared term, which is also negative, add them together and you get negative 0.0000908. Okay, so that's what you'll end up with. That's the moment of inertia of the disk. You want to do the same thing for the rectangle, the rectangular plate, and that's 0.000972. There it is. Oh, no, I don't want to do that. I want to get out of there. All right, where are we here? There we go. Okay. And then you just add the two together and you end up with a total moment of inertia. And that's 0.000881. Okay. So the one thing on this to remember is you can't shortcut the calculation process. You got to find the full moment of inertia of the entire of each entire part you're working with, and then combine them at the very end. You can't like cut a circle out of a rectangle, then find the moment of inertia for a rectangle with a circle cut out of it, because there's no table that'll tell you what that is. You got to take the full moment of inertia for the rectangle, full moment of inertia for the circle cut out, then combine them at the very end. It's just got to be that way. Yeah, question?
So if it was instead of a cutout with like a cylinder attached to the rectangle,
yeah,
would you do the same process but add it?
Yes. Yeah. Yeah. So this stuff is just, I don't know what it's additive. You know, the composite figures. You just find the moment of inertia of each piece about that axis, and then add everything up. That's it. Okay. Other questions? Okay. All right. All right, so that's the deal with that. So there's 5 of them due, those 2 relative acceleration problems, which I seem to remember 311 and 312 is what I recollect. I'm not 100% on that, but I think they are. And then these 3, and those are due Monday. Okay. Okay.
I only have these 3 that we just did on Monday, and then 331, 332 on Wednesday.
Yeah, that relative acceleration, I signed that as well, though, I'm pretty sure. Why don't we have a look? Because we went over it. Did we go over that? I'm sorry, I'm kind of losing track here. Yeah, we went over that on Tuesday, right, before we did the review. So I'm pretty sure I've got those due.
311.
Yeah, 311 and 12. And they're due Monday?
Yeah.
Okay, that's what I thought. Okay. So let's finish up this translational stuff. Yeah, 311 and 312 are, they're just relative acceleration. They did take a little while. We went over them Tuesday, and I've got a pretty good, you know, the keys on them are pretty thorough if you need to refer to those. And we went over them pretty thoroughly too.
What is the focus one did?
I'm sorry?
When was this one did?
Oh, that one's due Wednesday. I pushed that one back a bit. Yeah, that one's due Wednesday, so we'll probably cover that on Tuesday. But actually, some of the stuff we'll cover here right now will relate to 311, or whatever that is, 331, 332. Okay. All right, so let's have a look at this one. What we got here, we got a motorcycle and a motorcycle rider. They're going down a hill. Oh, wait a minute, did I? Yeah, those are due. Okay, that's good. All right. And they're going to accelerate up the hill. And we want to figure out what that acceleration can be before they tip. All right, and this is page 700, I think it is.
It is.
Okay, thanks. All right, so, okay, we got a 12-degree hill. We've got all the dimensions there kind of on the angle, so we're using that kind of inclined axes. I went ahead and found the masses of the rider and the motorcycle. So I'm going to treat this as two centers of gravity, one for the rider, one for the motorcycle. The motorcycle is putting on the brakes, so as a result of that, it's accelerating. Now it's accelerating back. Okay, so that's what's happening there. So you tip in the opposite direction of acceleration. So if this thing's accelerating up that incline, the tipping will occur that way. All right, so I've got that. And then I went through and did some trig on this. I took cosine and sine of 12 times the weight of the rider and the weight of the motorcycle, and got the different components acting. And then I went ahead and put those on the sketch. So a lot of this stuff has been set up for you, okay? But this is the kind of stuff you'd have to do on a homework problem or whatever to get it set up. So find the mass and the weight both. Kind of determine what you're trying to do here. In this case, we're trying to figure out the maximum acceleration before tipping, and then figure out your axis system. We're on an incline here, so we're going with an inclined axis system. And then get yourself a good free body diagram that includes the accelerations. So I went ahead and did some trig there to get those weights broken into components, normal and parallel to the ramp, to that ramp or incline or whatever it is you want to call it. Okay. So we got acceleration going that way, tipping that way. If it's going to tip that way, it's going to tip about A. Okay, so that's the assumption that I would make there, of course. And right before it tips, I'm going to just analyze for that instant. The normal at B goes to 0. That back wheel is going to get very, very light just before it tips. So that normal force on it will go to 0. So that's one of the key assumptions I'm making there. Okay. I'll have some friction acting like that at A. I probably should have included that on my free body diagram. And, you know, when I do that, when I include that, it doesn't affect too much because I'm going to take moments about that lower wheel there at A. But all the same, to make a complete free body diagram, I probably ought to get that in there. So there's force of friction doing that. Okay. Now I won't put one at B because I'm assuming that normal goes to 0. So with no normal force at B, there wouldn't be any friction there either. Okay. So what I'm finding there is kind of that boundary of that place where just before it tips. So I'm going to assume that alpha goes to 0. As does AGY. They both go to 0. Okay. So do we got any questions on the setup on that? Because that's, it's a big part of the problem is getting all this stuff kind of understood and written down and sketch going and all that. So are we doing all right with that? All right. So what we got to do now is throw an equation at it, okay? And we can solve. We're going to set that back normal at b to 0. So what we want to solve for is a. So on account of that, I'm going to want to, excuse me, for not a being acceleration, okay? So I'm going to take moments about point A for two reasons. The first one is it'll eliminate the friction from my equation, so I won't have to worry about that. And also it'll eliminate the normal at A from my equation too. So if I take moments about that point, I'll take those two unknowns out that I don't really want or need to know, and then I can just solve directly for the acceleration up the ramp. I've got that A shown twice, but there are two, but they're equal to one another, so they're really just one unknown. So I'm treating the rider and the motorcycle separately. So rather than finding a composite center of gravity here, I'm just treating them as two different ones, okay? So it's just a matter of throwing this equation here at it, okay? So, what do we got there on the left? We got the static stuff, okay? That's what goes on the left. Static stuff are the weights, forces, okay? They go on the left. And then the dynamic stuff on the right, okay? So everything on its proper side of the equation and everything with the proper sign. Now, what would I call positive here for moment? It really doesn't matter what I do as long as I'm consistent, but I could, I don't know, is counterclockwise, is that a good way to go with positive? It's tipping that way. I guess that'll work, okay? Now, you could call either one you want positive. As long as you stick with it, it doesn't matter. All right? So I got a whole bunch of stuff going on there. And I'll just write them down. I got 291 newtons. I won't even bother with signs just yet. Then I got 1369 newtons. And then I've got 133 newtons. And then I've got 626 newtons, okay? So I've got all those four different components of weight, 2 for the motorcycle, 2 for the rider. And then I've got moment arms. Now to make a moment, you combine unlike things. So that 291 newtons, that'll get combined with 0.4 meters. And that's going to go counterclockwise, so that looks like a positive to me about A. Okay? So I got an X force and a Y moment arm. Then I got a Y force, 1369, and an X moment arm of 0.7. That's going to go clockwise about A, so that'll get a negative. Okay? And you just kind of go through and have a look at them, and get them all worked out. The 133 looks a lot like a positive there. That's an X force. 0.4 and 0.76 ought to be 1.16 meters. That ought to be a positive. And then that 626 looks like 0.7 and 0.3 ought to be about 1.0 meters. And that ought to be, what, is that a negative there? Okay. So there's the statics side. If you were just doing a statics equation, you'd have that in there for a moment, okay? Now the dynamics are the inertial moments, they call them. Mass times acceleration times momentarm. Can't remember the masses on these. Let's have a look. 1,406, no, those are weights. 142.71 and 65.24. Okay. So what I'm going to do there is I'm just going to put together two terms, mass times acceleration. Now the acceleration is the unknown, and then a momentarm, okay? And then I'll have another mass times an acceleration, which is the unknown, times a momentarm. Now, why don't you get those two filled in? We got 2 minutes, so why don't you just take that time. They're the red A's. Get the mass in there and get the momentarm. Get the sign on those things, okay? Y'all getting to that okay? So they're both negative because they're both going to go clockwise around A. Instead of looking at the direction of force, you look at the direction of acceleration. They're both X accelerations, so you use Y moment arms. 0.4 for the lower one, 1.16 for the upper one. So negative 142.7 times A times 0.4 and negative 65.24 times A times 1.16. Doing all right with that? Okay.
Is it just a coincidence it's close to gravity?
Yeah. Yeah, it's pure coincidence it's close to gravity. They're just made up numbers. So. I don't know, how many G's do they train fighter pilots for, like doing loops and stuff? Anybody know? It's like 1 G. Definitely more than one. They go, yeah, they go way over that, yeah. So anyways, this is 1 G. As they call it, so we good with this? Doing all right. And then I already signed those two to you already. They're due Wednesday. We'll cover them on Tuesday. I think it's 331 and 2. Okay. So we got 5 of them due Monday. The 2 relative acceleration, and then the 3 moment of inertia that went over today, and then we got these 2 due Wednesday. We probably get to something else on Monday too. We'll see. Okay. All right. There we go. Hope everybody has a good weekend.